Hello and welcome to the first video in a series where I will be doing solutions and walkthroughs of past paper questions. These past paper questions come specifically from the IB Diploma Program for Maths Analysis and Approach, and I'll be doing higher level and standard level questions. In this video, I'm going to be looking at a question from May 2021 Higher Level Paper 1, Question 2. And this question is worth 7 marks. In this question, we have 2 cosine squared x plus 5 sine x is equal to 4. So a trigonometric equation where we're looking for x between 0 and 2 pi. Now typically when we have an equation with 2 different trig functions, we want to put it in terms of one trig function or the same trig function. So right off the bat, I can see that cosine squared x is part of an identity, and that identity is cos squared x plus sine squared x is equal to 1. And I want to put this in terms of cos squared x. So I can get cos squared x is equal to 1 minus sine squared x. And now I can plug this into my original equation. So I will get 2, and then in brackets, 1 minus sine squared x, because cosine squared x is equal to 1 minus sine squared x. It's the same thing. So I can plug that in. And then I have plus 5 sine x is equal to 4. What I can do now is expand this. So I can get 2 minus 2 sine squared x plus 5 sine x is equal to 4. And now what I can do is I can turn this into a quadratic. So I'm going to bring my sine squared x onto the other side here. So I will get 2 sine squared x minus 5 sine x, and then I will get 4 minus 2, so plus 2 is equal to 0. Now once we have this quadratic, what I like to do is I like to sub the trig function for a variable. So I'm going to make y equal to sine x. So what I can do is I can sub in y for sine x, and then I'll have a simple quadratic. So I'll have 2y squared minus 5y plus 2 is equal to 0. And now you can factorize this quadratic like you would with any other quadratic. Now, if you're curious, I have a video on this already, and feel free to check that out if you don't already know how to do this. So I am going to factorize this right now. X. And my factorized form of this quadratic will give me y minus 2 and 2y minus 1. And we're going to set that equal to 0. You probably noticed, but my pen is running out of ink, so I have a new pen now. So anyway, once we have this quadratic, we can then sub in our sine x into this quadratic. So we're going to get sine x, that's a lot better, minus 2, and 2 sine x minus 1 is equal to 0. So once we have this, we can solve each bracket individually for 0. So we're going to get sine x minus 2 is equal to 0, and 2 sine x minus 1 is equal to 0. So this equation will make sine x equal to 2, and this equation will make sine x equal to a half. Okay. Now, this actually isn't our final answer, because we still need to find out what x can be equal to. Once we've plugged it in, it will give these values. So let's take a look at our sine x function as by itself. So we can draw the sine function like this. And at here, this is equal to 0. Here, this is equal to pi. And here is equal to 2 pi. As a full cycle is 2 pi, and a half is pi. Now, the question we're asking here is, at what point of x does it give 2 or a half? Now, if you're familiar with the sine or cosine function, you know that the highest point So the peak and the trough of the function only reach 1 and -1. So we know that sine x cannot be equal to 2. So no matter what value for x we plug in here, it cannot equal 2. So we know that sine x equal to 2 is not a solution. This means that our equation that we should be looking at is sine x is equal to a half. Now as you can see here, I put 2 dots where y will be equal to a half. And what we want to find is the x value for our sine function that gives us a half. Now, as a DP student, you need to know exact trig values for sine, cosine, and tangent, but I will save you some time and tell you that sine of 30 is equal to a half. Now, sine 30, this is in degrees, right? And our domain here is in radians. So 30 will be pi over 6 in radians. So a 6 pi. And that is this solution right here. However, as you can see, there's another solution when we get closer to pi. And the reason for this is that when we have our unit circle here, and this is for our sine function, we know that this is split into, you could say, 4 regions right here. So this is from 0 to pi over 2 to pi to 3 pi over 2 and then 2 pi. So these 4 regions, we can show that this is positive, this is also positive, this is negative, and this is negative. Now we know our solution is positive because we know it's a half. So we know it's in these 2 areas, right? So what we can say is pi over 6 is our first answer, so that's this one right here, around here. But we also need to know this one. So what we can do is we can do pi minus pi over 6 to find our other solution. And that's going to give us 5 pi over 6 for our second solution. Because we know that this angle here is pi over 6. So if we rotate it all the way around here and minus that angle, that will give us the exact same solution for the sine function. So our 2 solutions between 0 and 2 pi for this equation will be pi over 6 and 5 pi over 6. And this works because in this region, the second region, you can see that it's actually a mirror of the first region. It's only flipped, meaning that all these angles here are reflected here. And the same goes for the third and fourth quadrant. These angles here are also reflected here, meaning we have 2 solutions for 0 and 2 pi. Thank you for watching, and I'll see you all in the next one.